Hey, today we're going to talk about extrema of functions. We have to start with a handful of definitions that might seem confusing or intimidating at first. Hang in there. As soon as I show you a few examples, you will completely understand what's going on. Not difficult at all. And here they come. The first definition is that of an absolute maximum. We say that a function f has an absolute maximum at some point c. If the function value at c is greater than or equal to the function value for all other points x in the domain of the function. And we call that function value the absolute maximum value of the function f. And we have a completely analogous definition for an absolute minimum. Same idea, except that the function value is less than or equal to the function values for all the other points in the domain of the function. And we call this point f of c the absolute minimum value of the function. And then we have this concept of a relative maximum, sometimes called a local maximum. We say that a function f has a relative or local maximum at some point c if the function value at c is greater than or equal to the function value for all points x in some open interval containing the point c. Show you a little bit more about what that means in just a moment. And then, of course, there's the analogous definition for a relative or local minimum. A function has a local minimum at some point c if the function value at c is less than or equal to the function values at all points in some open interval containing c. Okay, those were the definitions. Let's look at an example. Let's look at the graph of the function y equals x squared. This function has an absolute minimum at x equals 0, and the absolute minimum value is the function value at 0, which is 0. And you can see that that's true because the function value at 0 is smaller than the function value anywhere else in the entire domain of the function, which is all the real numbers. On the other hand, this function does not have any absolute maximum value. It keeps getting larger and larger and larger, and so there is no number, there is no x value such that the function value there is the largest possible function value that this function x squared ever attains. The absolute minimum at x equals 0 is also a relative minimum at x equals 0 because there's some open interval, like say this one right here, where the function value at 0 is less than or equal to the function value for any x values in that interval. And by an open interval, we mean the interval of all the real numbers between two specific real numbers. I'm calling them a and b here, but not including the endpoints. So all the points between a and b, but not including a and b. And the interval notation for that is, as you see here, with parentheses, that shows that the endpoints are not included. If instead we look at the function y equals x squared, but restricted to the domain -1 to 2, including the -1 and including the 2, then it still has an absolute minimum at 0, which is still a relative minimum at 0, but it also has an absolute maximum at x equals 2. This function reaches an absolute maximum value of 4 at x equals 2. There's nowhere else that this function attains any higher value. And it's worth noting that the point at x equals 2 is not a relative maximum because there is no open interval containing 2 on which this function is defined. An open interval containing 2 would have to have points to both the left and the right of 2, and the function's not defined to the right of 2. If we look at the graph of the cosine of x as another example, then it has infinitely many absolute and relative maxima and minima. And for example, there's an absolute and relative maximum at 0, and at 2 pi, and at 4 pi, and at 6 pi. You can't see those on the graph, but they're there. They're both absolute maxima and relative maxima. And there are absolute and relative minima at -pi and 3 pi and on and on and on forever. So infinitely many absolute and relative extrema. And I'll say it again just because it's worth saying. The point at x equals 2 pi, y equals 1 is both an absolute maximum for this function and a relative maximum for this function. It's the largest function value in some open interval containing 2 pi, and it's also the largest function value that the function attains anywhere. And let's look at one more function, the polynomial function f of x equals x cubed minus 12x plus 10. It has some relative extrema, a relative maximum and a relative minimum, that are not absolute extrema. In other words, the relative maximum that we see on the left is not the largest value that the function hits anywhere. It's the largest value that the function hits in some open interval. But if you look over to the right, you can see clearly that the function does hit larger values somewhere else. And the relative minimum that we see over on the right is the smallest value that the function hits in some open interval, but not the smallest value that the function hits anywhere. You can see that over on the left, the function hits smaller values. And if you were to estimate the slope of a tangent line at the places where this function has a relative maximum or a relative minimum, well, you would see that the tangent line is horizontal in those places and so has a slope of 0. And so the derivative at the places where this function has a relative maximum or minimum is equal to 0. And we'll prove this more carefully in the future, but it is a theorem that if you have a differentiable function with a relative extremum, meaning a relative maximum or a relative minimum at some point c, then the derivative at that point c is equal to 0. And suppose we look at the function that we were just looking at, f of x equals x cubed minus 12x plus 10. It's very easy to compute the derivative of that function. It's 3x squared minus 12. And if we want to know where the derivative is 0, that would be asking where 3x squared minus 12 is equal to 0. And you do a little algebra to solve that equation, and you find that it happens when x is positive and negative 2. And if you look back at our graph of this function, I didn't want to make any assumptions before we had done the work to show what was really going on, but the relative maximum occurs at x equals negative 2, and the relative minimum really does occur at x equals positive 2. Now let's look at a second example, this polynomial here. And it's a polynomial, so it's very easy to take the derivative. And if you plug x equals 1 into the derivative, you find that the derivative at 1 is equal to 0. But take a look at the graph of this function. At x equals 1, well, the derivative is 0 there because a tangent line is horizontal there. So the slope of a tangent line is 0 there. But there is neither a relative maximum nor a relative minimum at that point. At x equals 1, if you look to the left, the points are higher. And if you look to the right, the points are lower. And so it's not a relative maximum or a relative minimum. And I showed you that example to emphasize that the theorem says that if the function has a relative extremum at some point, then the derivative is 0. It does not work the other way around. If the derivative is 0, then the function may or may not have a relative extremum at the point where the derivative is 0. We've seen both kinds of examples just a moment ago. We're going to be very interested in finding both the relative and absolute extrema of functions. For relative extrema, we've already seen that you have to look at the places where the derivative is 0. We also have to look at the places where the function is not differentiable. The theorem that we just looked at assumed that the function was differentiable. If it's not differentiable at some point, could have a relative extremum there. For absolute extrema, we're also going to have to consider the endpoints of the domain. Those won't play a part in our search for relative extrema because the endpoints of the domain are not enclosed in any open interval, including those points. Which is to say that in our search for relative extrema, we're going to be very interested in the places where the derivative is 0, or the derivative doesn't exist, meaning where the derivative is 0 or where the function is not differentiable. We call those places critical points for the function, or sometimes critical numbers for the function. X equals c is a critical point, or c is a critical number for the function if the derivative at c is 0 or the function is not differentiable at c. Okay, you try this. Find all the critical points for the function f of x equals x squared plus 7x plus 3. Pause the video, take a moment. When you're ready, start it back up. We're looking for all the places where this function is either not differentiable or where the derivative is 0. It's a polynomial, so it's differentiable everywhere. And so all we're looking for are the places where the derivative is 0. Well, the derivative of this function is 2x plus 7. And if you want to know where that's equal to 0, you set it equal to 0 and solve for x. And you easily find that x equals negative 7 halves is the only critical point for this function. We know that if the function has a relative extremum, it has to occur at a critical point. And so if the function has a relative extremum, it must be at negative 7 halves. This function is a parabola. It does have a relative extremum. It's a parabola, and because the leading coefficient is positive, it goes up on the left and the right, and so it has a relative minimum, which we usually refer to as the vertex of the parabola, and we just found it. It's at negative 7 halves. Okay, try one more. Find all the critical points for the function f of x equals ax squared plus bx plus c, where a, b, and c are constants and a is not equal to 0. So take a couple of moments, pause the video, see if you can figure that out, and then we'll do it together. As before, this is a polynomial, and so it's differentiable everywhere, and so the critical points are only going to be where the derivative is equal to 0. The derivative is 2ax plus b, and to figure out where that's equal to 0, we set it equal to 0 and solve for x. And you do a tiny bit of algebra, and you find out that this happens when x equals negative b over 2a. Which maybe looks familiar to you. What we've just done is determine the formula for the vertex of a parabola. It always annoyed me that in algebra classes they tortured people with memorizing this formula. This is a very simple calculus problem. Have a little patience, wait till you know a little calculus, and then you can just figure this out using basic principles. Okay, we're going to be doing a lot of finding extrema of functions in the near future. There's a homework on this stuff. It's mostly of the here's a function, find the critical points variety. Give that a shot, have some fun with it, and I'll see you soon.